We present our work Unsupervised Sketch Photosynthesis. Sketches are rapidly executed freehand drawing. They make an intuitive and powerful visual expression. A lot of research has been done on sketches. For example, recognizing what the sketch is, segmenting a sketch into object parts, and retrieving relevant photos according to a sketch. Humans can envision a realistic photo. Our work is to enable a computer to do the same, that is, synthesizing a photo given a freehand sketch. Sketch photosynthesis is challenging. First, to synthesize a photo from a colorless and textureless sketch, a lot of appearance details must be filled in properly. Second, sketches have large spatial and geometrical distortion. Therefore, translating a sketch to a photo requires shape rectification. However, rectifying shape distortion is not trivial because sketches exhibit different drawing styles. Many line drawing to photo translation methods have been proposed for different settings. The most studied case of line drawings is edge maps. Since they are derived from images, the lines align with the intensity contrast change in the photo. Pix-to-Pix requires paired data for training and it synthesizes photos from the edge maps. CycleGAN and MUNIT do not rely on paired data, but they still assume aligned edge maps. We consider freehand sketches and photos, which are not aligned, and without paired training data. We will show that existing methods fail in this task. Our key insight is to introduce an intermediate synthesis goal and decompose this task into two separate translation stages, shape translation and content enrichment. The shape translation network learns to synthesize a grayscale photo given a sketch. Geometrical distortions are eliminated at this step. Content enrichment learns to fill the grayscale image with colorful details. It is designed to work with or without a reference image, so that it can produce diverse outputs. We first show our sample results. The input sketches are from Shoe V2 and Chair V2 datasets. Our synthesized photos are realistic and faithful to the sketches. When provided a reference image as shown at the right upper corner, our model can output a new photo faithful to the sketch but in a style similar to the reference. We compare our results with existing works which all adopt one-stage translation. Let's focus on quantity comparison in the third row. While Pix-to-Pix uses pair training data, misalignment between a sketch and its corresponding photo results in very poor fidelity in translation. Also, if we compare row 3 and 4, their sketches are drastically different, but Pix-to-Pix synthesized photos are highly similar. CycleGAN and MUNIT have better fidelity to the sketch, but they contain artifacts such as holes and are not photorealistic. Again, the misalignment between sketches and photos poses additional challenge when the training data are not paired. UGATIT can generate much more natural-looking photos. Its key is to use an attention module to locate the regions critical for translation. However, is synthesis not faithful to the input sketch, it can only produce a single output. Our model can generate photos with high fidelity, photorealism, and diversity. Additionally, our shape translation model is bidirectional. We can also translate a photo into a sketch. This task is not trivial, as users can easily detect a fake sketch based on its stroke continuity and consistency. Our model can work as a sketch extractor, creating line drawings that mimic freehand sketches and emphasize contours that are perceptually significant. Our model works well on novel categories other than the one it is trained on. Canny edge detector is handcrafted and its edges indicate low-level intensity gradients. HED is a deep learning-based edge detector trained to output external object boundaries. Photo sketching learns from photo line tracings generated by humans. Its lines indicate both interior and external contours, which are continuous and perceptually salient. Our model is trained exclusively on shoes, yet it outputs plausible and realistic sketches for these non-shoe categories. A direct application of our model is unsupervised sketch-based image retrieval, where the key challenge is cross-domain comparisons. With our model, we can easily translate sketches and photos into the same domain and perform same domain comparisons. We can accomplish this diagonal cross-domain retrieval in two different ways. One goes through the top and the other goes through the bottom. We can translate all the gallery photos to the sketches using our model. We perform query-to-gallery retrieval in the sketch domain and then find the corresponding photos. Alternatively, we can translate the query sketch to a photo and conduct retrieval in the photo domain. Our experimental results show that the first approach is better by 10% in the top 5 accuracy. Next, we introduce technical details of our model. At stage 1, our shape translation network is built upon basic CycleGAN. CycleGAN can handle simple sketch to photo translation well, even when the training data are unpaired. However, since sketches drawn by different users have different levels of abstraction and different drawing styles, some sketches could have distractive or noisy strokes, and those are really troublesome for CycleGAN. We refer to sketches with complex or distractive strokes as noise sketch. We introduce 3 technical mechanisms to handle these noise sketches, including noise sketch composition, a self-supervised objective, and an attention module. Our first strategy is to compose additional noise sketches for training data augmentation. We compose new sketches by adding noise to the original sketches. The noise can be either complex strokes or random patches extracted from the original sketches. We introduce a self-supervised denoising objective so that the model could recognize what is content relevant and what is style variation. For an untouched original sketch, the model aims to reconstruct the input sketch with the cycle consistency loss. For a composed noise sketch, the model aims to reproduce the original clean sketch with our self-supervised denoising loss. Our model learns to ignore irrelevant strokes and put more efforts on style invariant strokes in the sketch. In addition to the self-supervised objective, we also introduce an attention module to identify distracting strokes. Since most areas of a sketch are blank, the activation is stronger in dense stroke regions. We can thus locate and suppress the activation there accordingly. Once the feature activation of distracting region is weakened, the model can generate much better results. The total loss at stage 1 thus includes adversary loss, the self-supervision loss, the consistency loss, and the identity loss. At stage 2, our content enrichment model is based on an encoder-decoder architecture. In order to generate diverse outputs and increase users' control on the output, we integrate an ADIM module to accept a reference image for synthesis. We adopt a mixed training strategy so that the model can work with or without a reference. When there is no reference image, only intensity loss and adversary loss are used. Otherwise, a content loss and a style loss are computed additionally. Our extensive experimentation demonstrates that our model can generate more photorealistic, sketch-faithful, and diverse photos than existing methods. We are better than all the baseline on all the evaluation metrics except MUNIT on the LPIPS, which measures diversity. Our outputs are only different in colors and texture details for an input sketch. However, MUNIT allows the shape to change as well. It achieves more photo diversity at the cost of losing fidelity to the input sketch. We train exclusively on SUV2 and test on new datasets where the sketches become more abstract. Sketchy has sketch and photo pairs, whereas TU Berlin and QuickDraw have time unlimited and time limited conceptual drawings produced based on semantic labels. Our model generalizes very well to new datasets without any fine-tuning. We test our shoe model on sketches from other categories. For a non-shoe sketch, our model translates it into a shoe-like photo. Since our model is bidirectional, we can also translate the photo back to a sketch. The overlay of our reconstructed sketch and original sketch shows how our model selects and modifies the strokes in a non-shoe sketch. Finally, we provide 3 insights from our ablation study. We found out that our two-stage architecture is the key to the success of our model. Using grayscale images as the intermediate synthesis goal is better than using the edge maps. And our shape translation network in fact achieves better performance in the unpaired training setting than the paired setting. For further details, please refer to our paper and project page.